Okay, so today we're talking about the absolute value function. This one is a parent graph. It's one you almost want to know by heart. I'm going to actually just derive a few of these points just by, plugging in some x values. I think we've done this before. 0, 1, 2, 3, -1, -2, -3. So let's plug in 0 first. That's usually easy to do. So if I plug in a 0 for x there, so that'd be the absolute value of 0, which is 0. So the point is 0, 0. So that's on this graph. Absolute value of 1 is 1, so 1 1 on this graph. Absolute value of 2 is 2. Absolute value just makes things positive, right? So 2 2. Absolute value of 3 is 3. And you can probably see as we go up higher, it's definitely looking pretty linear there, something like that. But let's try this. Absolute value of a negative number, -1, is actually a positive 1. So that's the point -1 1. Oh, that's a little change. Absolute value of -2 is going to come out positive, of course. It's going to be 2. So that's the point -2, comma 2. So -2, 2. And absolute value -3 is -3, 3. So the graph looks something like this. Okay, so that's the absolute value graph. It looks like a V. In fact, kind of a silly way to remember this is the absolute value function, right? Think of that V there, V in value. The shape of this graph is always going to be a V. It's kind of a silly way to remember it. But this basic paragraph is pretty easy to remember. 1 1, 2 2, 3 3, but then -1 1, -2 2, -3 3, and so forth. Okay, let's go to TNS file and see what this looks like. So this is the absolute value graph. This is the graph of y equals, this is written a little weird. 1, if you look down here, 1 times absolute value of x minus 0 plus 0. Now, if I change some of these values, if I change, say, h to 1, if you notice the equation is now says x minus 1, and it moved 1 to the right. If I change that to 2, let's see if I can do that. Now it moved 2 units to the right from the original, and it says absolute value of x minus 2. So do you have a guess what would happen if I move this, so h is -2 or -3? Now it says x plus 3 inside the absolute value bars. So it looks like changing that value inside of the absolute value, like either adding or subtracting. What's interesting is when you add 4, it moves to the left. When you subtract 4, it moves to the right. So subtracting a number moves to the right, adding, so it kind of works the opposite way you would think it would work. Let's look at this. So, well, this actually works. So when k is 2, it moves up 2. When k is, I guess, -4, it moves down 4. So this one moves things vertically. So that k value there at the end of the function, if I subtract something in, it goes down. If I add something, then it goes up. If it's just 0, it stays in the parent function. Now, a is really interesting. So if I change the coefficient in front of this function, if I make it a little bigger, can you see the graph is changing shape a little bit? The v is actually getting smaller. So the bigger that number, the skinnier the graph is going to get. And if I make it smaller, like a fraction, like 8/10, 6/10, 4/10, 2/10, that's a pretty small fraction. It's going to be very open, very wide. So it changes the shape of the graph. And watch what happens when it goes negative. It actually flips down. So that graph really reflects over the x-axis. If it's -1, it's a perfect reflection of the absolute value graph if that value is negative. So that's called a reflection across the x-axis. And again, as that gets smaller, it gets skinnier as that number absolute value grows. So the formula for this one is something like this. Y equals a times the absolute value of x minus h plus k. You want to write that down in your notes. You want to realize that h is going to move it horizontally, the opposite way you think it's going to go. K is going to move it vertically. And a does a couple of things. If it's negative, it's going to reflect across the x-axis. And if it's, say, a is bigger than 1, that's going to be called a vertical stretch. So it stretches it, makes it kind of skinny. I guess we could say this, if A is like between 1 and 0, as far as its absolute value, when A is really small, in other words, that's going to be called a vertical shrink. So it kind of makes it wider. Okay, so let's go to some problems and see if we can figure it out. So we like to do this by starting with the parent graph. So again, I have the parent graph memorized, 0, 0, 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2. I've got the parent graph. I'm just going to put dots there for the parent graph. That's our parent graph. Let's do this in 2 steps. So first, let's do the negative. So I like to go left to right. As I do these are called transformations of the graph. It's going to move it in some ways. In this case, the negative reflects over the x-axis. So if you take all those points and just kind of fold them down, this point will fold down to here. This point will fold down to here. This folds down to there. This one folds down there. This one folds there. That one goes here. And 0, 0, if you fold it over the x-axis or reflected, actually stays in the same spot. So now the V is kind of shaped downwards. So it kind of just reflected or kind of flipped it over the axis there. The plus 3, remember, it goes the opposite way you think. Instead of going to the right 3, it's going to go to the left 3 when you're adding a number. So I'm going to take all those red points there, and I'm going to make them all move to the left 3. 1, 2, 3, there's my point. 1, 2, 3, there's my point. 1, 2, 3, 1, 2, 3, 1, 2, 3. You kind of see the pattern now. It'd probably be enough to just graph it at this point. So the V, this is the final graph actually. I'm going to actually connect the dots here. And that's the graph of that absolute value function, negative absolute value of x plus 3. So it says identify the vertex. The vertex is the point, negative 3, 0. The axis of symmetry would be a dotted vertical line that goes through the vertex. And that looks to be a vertical line, so x equals negative 3. We talked about that the other day. Describe the transformations. If I had to describe those in words, this one is reflection across the x-axis. And the plus 3, I would say it moves it to the left 3 units, something like that. So that's what the transformations are. That means how does it change the graph or transform the graph. Okay, let's try this one. This is getting a little tougher. So when you have a number in front here, if it's not 1, that's going to change the shape of it. So you actually have to change those points. But you start with the parent graph. So again, we're always starting with the 0, 1, 1, those points we know and love. I'm not going to connect them, but that's the parent graph. Okay, so what I typically do, in fact, when you have a coefficient here, I like to write out those points. So I'm going to write out the points that I just graphed out actually there. So I'm going to write out the point 0, 0. 1, 1, 2, 2, 3, 3. I guess it'd be negative 1, 1, negative 2, 2, and negative 3, 3. Okay, so I wrote out all those points. And so what this thing does at the beginning is 1/2, is it's called the vertical stretch. And so it's vertically stretching it. So the y values are being affected. So all the y values are being multiplied by 1/2 in this case. So for a stretch or a shrink, you're going to multiply all the y values of the original parent function by a, whatever a is. In this case, a is 1/2. So all these, so 0 gets multiplied by 1/2. Well, 0 times 1/2 is still 0. 1 times 1/2 is 1/2. 1/2 times 2 is 1. Half of 3 is, I'm going to write it this way, 3 halves. Half of 1 is 1/2. Half of 2 is 1. Half of 3 is 3 halves, or 1.5. Okay, so I'm going to plot all those points now. So 0, 0 actually stays in the same spot, but the y values of these points are now cut in half. So it was 1, 1, now it's 1, 1/2. It was 2, 2, now it's 2, 1. It was 3, 3, now it's 3, 1.5. And so this part of the graph is kind of, if I drew kind of a dotted line there, this is not the final graph. Looks like that. Over on this side, similar things. We're going to plot those 3 points. And just so you see, like that's the kind of the the halfway point graph. This is not actually our full graph, but I got all the points there. I see what the shape of the graph definitely changed. It got wider. So then we're going to do the last transformation. So that's called a vertical stretch. And the last one, since it's outside the absolute value, it's going to move it down 2 units. So I'm going to take all of those points I just got in red, and I'm going to move every point down 2 units. This one goes down 2. It's kind of hard to do that. It's not on the nice point there, but you can do it. Got the half the graph. And this point goes down 2, and down 2. And I've got the other half of the graph, and there you go. That's our graph of the transform function. If you want to identify the vertex, that would be at 0, -2. The x-axis symmetry is a vertical line, so you know it's an x equals line. It's x equals 0. And if you describe the transformations as vertical stretch, and you move down 2. Hopefully you're getting the hang of this. There is a coefficient, so I am going to write out those ordered pairs. So I'll kind of graph them just so we have reference points there, but the parent graph ordered pairs for those are there. Let's start with 0, 0, 1, 1, 2, 2, 3, 3, -1, 1, -2, 2, and -3, 3. Okay, so we're going to transform those. So all the y values are going to be multiplied by 3. That's called a vertical stretch again. So that's going to be 0 still. Well, that's 3. That's 6. Wow, this is getting big. This is 9. That might be off the thing here. So this is 6 and this is 9, right? Just multiply all the y values because we're stretching the graph. The y values are being affected. So the shape of this will definitely change. So I need this graph paper is not going to work out well for this. I don't have enough points. 0, 0 is still there. 1, 3 is there. It's a little off the chart, but right up there at 2, 6 will be a point. There in -2, 6, again, right up off the chart, somewhere up there. So this graph is going up. I can't really graph any more points with this graph. It's going way up like that. Like that's kind of the look of this graph. It's quite a bit skinnier. I guess I should probably, it would have been a good idea to do that as a dotted line because that's not my final answer. I don't even have to connect those points, but I just want to see what it looks like. I wanted you to see that it definitely is getting skinnier here. And so then I'm going to take those points and we're going to transform. Oh, we've got 2 transformations. Let's try to do these both at once. So this one, it's subtracting inside, so it's going to go to the right, and subtracting outside is going to go down. So I'm going to go right 1 and down 4 with each of those points. So this point will go to the right 1 and 1, 2, 3, 4. This point will go to the right 1 and 1, 2, 3, 4 down. This point up there will go to the right 1 and 1, 2, 3, 4. I think that's right. To the right 1 and 1, 2, 3, 4. And then that vertex point will go to the right 1 and 1, 2, 3, 4. So I've got my points. It's kind of hard to graph on this, but that's my new absolute value graph, the transformed graph. This is going to be the point 1, -4. The axis of symmetry is a dotted vertical line that would be at x equals 1. You know it's an x equals line if it's vertical, and you got it. Hopefully you're getting it. We can do one more example here, but I think you're probably getting it. So you don't have to graph the points every time, but it's not a bad idea, especially when you're first starting out. And so 0, 0, 1, 1, 2, 2, 3, 3, -1, 1, -2, 2, and -3, 3. Okay, so I'm going to graph. I'm going to, oh wow, this does 2 things. So you can actually perform 2 things at once. Here's the beautiful. So if a is negative, I just multiply everything by -2, all the y values. So, well, that's still 0. 0 times -2. 1 times -2 is -2. -4, -6, -2, -4, and -6. So I'm going to plot those points. So 0, 0 stays in the same spot. 1, -2, -1, -2, 2, -4, -2, -4. I'm going to stop there. And then all those points get moved, right, or transformed. +3 inside the parentheses goes left. Outside the parentheses goes up when it's positive. Because it's x minus h, that's why it goes left. It's plus k, that's why it goes up. Okay, so left 3, up 1. So to the left 3, 1, 2, 3, up 1. To the left 3, 1, 2, 3, up 1. 1, 2, 3, up 1. And 1, 2, 3, up 1. 1, 2, 3, up 1. And you've got your graph, something like that. Pretty skinny, reflecting downwards. The vertex is at -3, 1. And the axis of symmetry is at x equals -3. Thanks.